Hi, everyone. Welcome to today's webinar for the gravity design of beams and one-way slabs. We're going to use a parking example today, a simplified example. I'll kind of talk about a few different options in modeling. Idealized parking ramps with steps, and we'll talk about kind of where we're going for the future. But the core of today's meeting will be mainly done in single level mode, assuming the ramp is flat. So we're recording today's session, and make sure to add that to our webinar YouTube playlist after we're done. If you have questions, again, please, if we can, we'll reserve those towards the end. Today's meeting will last about an hour with Q&A at the end, and then this is part one of part two. Part two next week will look more at modeling the post-tensioning in the beams and in the one-way slabs. And then also, if you have colleagues or folks that cannot attend, just make sure that they're aware of the YouTube option. So today we're going to start. If any of you have been involved in the webinars over the last couple of weeks, we've talked about importing from Revit and also from DWG. And today we're going to actually do something similar, but we want to talk about, we're going to use the model from the Revit file. And if we go to Revit, we have something that looks like this. This is just a fictitious parking structure, just to kind of show and give an example of how this is done. We also have a sample model here that actually has some ramping. So in this model, if we look at, for example, a side view, we can see we have offset slabs, offset columns, we have connecting elements, which are walls that are offset at the top and bottom. So this, I would say, is an extreme example in terms of how you would model or simulate ramping in today's version of the software. We do have a couple of YouTube videos that are just sneak peeks. We're actually introducing ramping in the 2019 version, where you can model a smooth ramp. It will be limited to only modeling the ramp and using the ramp for analysis. In the first release, you will not be able to add post-tensioning to the ramp in terms of if, for example, let me give you a little bit of a idea here. If this ramp, let's say you can model this as a smooth ramp, this can then be modeled as smooth. You can still model the post-tensioning in these beams that are carrying the ramp. So you can have PT in this case, in the X direction out of the screen, but we cannot model PT along the path of the ramp. So there will be that limitation in the first phase, but that's upcoming. In order to simulate ramping, you really have to take something like this and offset slabs. So if I switch this model to single level mode, you'll notice we have what it looks a little bit strange, because we have what appear to be floating walls at this particular level. This, if we start at the very base level, we have obviously columns, and we go up one level and we have two offset slabs. So this might be where the slab begins from grade, and then it starts to ramp up. And then we have walls that are shown on this level that are, the reason they're shown is because they're referenced back to level lower ramp right here. So if we double click on one of these walls, we could see that that wall, if we go to the location, the top of it is referenced from the ground level, the bottom is referenced from lower ramp. Therefore, it's shown at this level, even though there is no slab shown connected at this level. If I navigate up one level to ground, now we can see we have, again, another series of stepped slabs with offsets, and all of those offset slabs have to be connected somehow, and we use a wall element to connect them vertically. So this, why would we set up an example like this? We would mainly use this example for twofold. One is for lateral analysis, if you want to capture the continuity of the ramps for lateral purposes. then this is really the only workaround is to step slabs this way and segment them. And number two, if we have, I'll go up to this level here, for example. If we have a series of beams and there's a joint right here where we can see there and there, this beam is offset from this beam, and then you'll notice this beam and this beam are at the same elevation, so the tendon here can nicely transition into that beam. This is a condition where the offset is not too severe, where you technically could take a tendon, run it low on this side, and then dump it into that lower beam here. So this is a continuous path tendon. Once you get further downstream this way, then you have a tendon here, and you have another tendon here, and a third tendon. So now we have 3 tendons versus a continuous tendon. So if you're wanting to design beams with some of that continuity, then you have to go this route also. You could model beams and offset them and then model the tendons through. So this is an example. I would consider it an extreme example of taking ramping to the limit and how we can do it currently. We're going to kind of back up now and talk about, okay, maybe we just want to assume that the ramps are flat. We're going to discontinue the ramp, or let's say disconnect the ramp slab from the parking slab by adding an opening, maybe along the joint. And we'll take a look now at that type of a scenario. So I have sample models of this type of construction. If any of you want to see those, feel free to contact us afterwards, and I can send you an example model of something like this, and you can follow that maybe in building out some of the models that you're working on. Now we're going to go transition over to this model, and this is a model we're going to work on. I have it in Revit and also in CAD, and a few of the main objectives today. We're going to talk about generation. Again, this is part 1 of 2. We'll talk about generation of the model through the Revit and drawing file. I think we've seen this enough, the Revit link option, to where we can produce the IMP file and then import that into Builder. The drawing file in this case is a little bit different than what we've seen in the last 2 webinars, so I'm going to talk more about converting this particular drawing file. It will seem more tedious than what we've done in the past, but we're trying to cover different conditions and different styles of CAD files that are imported into Builder and understanding how those can be converted. We're going to add some loads and define combinations and criteria to this model today, and then we're going to model support lines and get this set up for processing the one-way slab and also the beams. So we'll go ahead and we're going to start just by taking this as a Revit file. Now in this model, you can see all of the levels are flat. If I go to a front view, everything here is idealized as flat. In reality, if we go and look at a level, we'll look at level 3, that's a level we'll work on. We have a system here where we have ramping starting here and ramping, let's say, starting here. So between this level, which is flat, and out here, which is flat, we have a break in the slabs. And to simulate the break, we've actually added an opening along this path and an opening along this path. Okay, and the beams, there's a column. So if I blow this joint up right here, we're going to have a column with a beam which frames to center line of column. And then the opening actually stops at the face of the column so that we can mesh this joint and it's meshed through. Otherwise, if you have the opening floating through the column, there's a possibility that the nodes of the beams and the column actually shift to one side or the other, and the other side or the opposite side that's shifted from is disconnected. That would become evident after you run the analysis and you see large displacements in that region where this joint wouldn't be connected. So let's go ahead and export this. I'll go up to Analyze. We're going to export this file. And we've talked about this in previous webinars. Here, this will show us which levels are going to be exported, the components to be exported in any load cases and combos. I'm going to actually take these combos and I'll dump those back over here. We'll define those inside of Builder. And we'll call this to adapt. Okay, and then over on the adapt side, I'll go up to File, Import, IMP, and we'll say this is to adapt, and we're going to import everything. Now in this dialog menu, you have different options that would allow you to update a level. You could import a entire model. If you already have a model in place, then it's not a good idea to create a new model, because that will basically dump a new set of components right on top of the model that's already in place. So this is really only for new versus for updating. If you want to update a level that's already existing, then we would select update, and then you can filter out any components that you do not wish to update. Okay, this also will show loads, load cases, and combos. We'll go ahead and import that. And you can see that if I navigate to level 3, for example, let me just go to P3 in single level. The way that the opening was represented inside of Revit was to face of column. Here, this actually floats through. So we want to be careful that, you know, when we analyze and mesh this, you're going to see the nodes shift to one side or the other, because a node, if we look at this, the shell elements will be aligned on this edge of the opening. They can't cross through the opening because it's an opening. We don't want to have anything going on there analytically in terms of the discretization of the elements. So we have something like this, and I'll put nodes in blue. So we're going to have a node here, we'll have a node there. These are the shell element nodes for the slab. And we're also going to have a node here at the centroid of this column, which also coincides with the endpoints of each of the beams on either side. So in order to connect these components, this center node has to shift to one side or the other. It can't stay there. We don't create a link between this node and this node. This thing right here, this center node or group of center nodes, gets shifted to one of the slab nodes. That still is okay as long as the slab is actually connected through the beam, which in this case it is. You'll see that here in a moment. So be careful of this modeling. There are some conditions where, for example, if I take these beams and if I move the beam, let's say to face of column, like so, now what could happen potentially is this beam could potentially jump over this gap and maybe get shifted to this edge of this opening here, and the column gets shifted and this beam gets shifted all to that node, and then this slab could potentially become disconnected from the beam. So there's ways to handle that. One way would be to split the column, which doesn't always work because you want the column to be representing the actual stiffness and length and size of the real physical column. So if I take this column and I split it, one to each side, this is probably the most direct way of maintaining, you know, connectivity in how these types of models are built. We would then have a beam maybe that goes to center and a beam that goes to center. This would avoid any issues with connectivity, this type of thing, but many times clients don't want to split the column. So another option would be to model the opening as it was shown in Revit, where the opening actually models to the face of the column. And by doing that, we're going to have an actual a slab element inside of that joint that's passing through. So that's another way to maintain the connectivity. You typically will end up getting more elements. You'll get kind of densification of the mesh in that zone at each column, so you'll end up having more shell elements in that case. But again, here this is created to connect these two slabs, and then we just flatten the ramp slab, which in this case is up here on the top side. This is the parking slab. This joint is just arbitrary. I think it's around 6 inches, maybe 6 to 12 inches in this case. The shorter it is in terms of its dimension, I'll call this dimension Y. If that dimension is 1 inch, then what happens is you get, I would call it severe densification of the mesh, because the mesh size is dictated in a way by this dimension. As we creep towards this opening, the program has to mesh due to the way it's constrained in terms of its algorithm. It meshes along that edge. So you're going to get kind of a step down to that size. And if that size continues to get smaller and smaller and smaller, you're going to get more and more elements. So if you're trying to avoid that, then just grow the size of that opening arbitrarily. All right, so this is what it looks like bringing it in from Revit. I'm actually going to import a CAD file. I would call this CAD file less than desirable. I actually created the CAD file from exporting it from the Revit model. So we're going to give you an example of a poor CAD file and how we can work with the CAD file to get this thing built also, if this is something that you do in your work. So we'll go ahead and let me just create a new file. And I'll import a DWG file. I'll calibrate this. And to calibrate, I'm going to just select this column. It's 22 inches. So I'll use my snap tools from point A to point B. We'll call this in feet. It's 1.83 feet. And say OK, and then I'm going to just zoom extents to bring that in. Now, anything that's a CAD or that's a polygon can be converted using model transform. You can see everything here is lines. And when you have a lot of beams, this becomes a little more tedious to deal with. The first thing I can do is actually convert my columns to my column lines to columns, but you can see this is kind of a strange shape for a column. This is how it came in from Revit. In reality, it's something like this. So there are a few things we can do to convert lines to polygons to begin with, and I'll do that for as many columns as I can. I'm going to just isolate this one layer. If I double click on that line, go to S columns, I'll use my layer settings option under the home menu, and I'm going to isolate. I'll turn everything off, turn this back on, and now I can just window select those lines, and using the model transform, I can transform those lines into a polygon. And 40 polygons are created. These ones here are, those strange shapes, but we'll just now reselect everything and convert those to columns. You can see this actually converts the out-to-out dimension of that strange polygon. So this still is okay. So we do our columns that way. That's easy enough to convert columns. I'll go back and turn all of my layers back on. And we know that creating a slab in this case would be easy enough. We can just create it based on the corner columns. That's in this case what the slab looks like and is positioned as. So I'll just create my slab by defining it using model and add a slab. Okay, there's my slab. The same thing can be done for openings. You can see these are just lines, so I'll just use the opening option here. Manually create my opening. And I don't really have to do the second one. I could copy it. So if I select my opening, and I can go to modify, copy in plane, and I'll just copy it from let's say the center of the column over to center of column. We'll say copy, and I have my other opening in place. So just systematically going through and developing this model. Now the beams are a little bit more challenging only because they're not a polygon. There's not a line that defines this side of the beam right here. So if I had a line, let's say here, and down on the opposite end, I could isolate all of the beams and then convert them to polygons and convert those to beams. In this case, that's not so. Now, so we have to basically draw in all of our beams by using our columns. We define the columns first so we can snap to their centers, and I can now just go in to model beam, and I'm going to snap to the center of that column. I'll actually go up here to properties and change the beam. I think it's a, let's see, I think it's 18 by 36, something like that. Okay, so we'll model beam 1, beam 2, and again, the lines that are there representing beams are basically useless to us in this case because we can't really convert them. So we end up essentially having to draw the beams in this case. If they were polygons, we could convert them, but here they're not, so that's okay. We can now take this. I'm going to press Control and then Control Tab to select the other beam. The beams will show up. The structural beams are represented by this X. That means it's a structural component. So if I just press Tab, I can select those. And now we'll just use copy paste, and I can copy those, to each column line, something like that. Okay, so this is just an example of a CAD file that has 0 polygons, and we have to use it to generate a model. Once I have my beams in place, there's also a beam that runs down the middle. I'll leave that one as is. I'm going to turn off the CAD file, which is stored in the group library under the visibility tab, and I'll define my levels. I'm going to add 3 more levels here, and I can now take this and modify it by copying it vertically. So I'll copy this up another 5 times, and if I go back to multi-level mode, we have a multiple level model based on that CAD file and converting that CAD file. Okay, so that's a little bit trickier, I think, if the CAD file is not set up in a way that it can easily be converted to a structural model. You have to jump through some more hoops. You might have to use construction lines to get things in there that you want, but that's an example of converting the CAD file. Now I'm actually going to go back to my model that was imported from Revit. So I'll import that IMP file again, and we'll start with that file. So this is the file we want. It looks almost identical to what we had just modeled, and we're going to focus, in this case, we're going to focus just on level 3. All the levels are typical. We'll go down to P3, single level mode, and we want to first set up, coming back to our cheat sheet here, we generated the model. We're going to now add some loads, define combinations and criteria. If you want to add loads to the entire structure, then it has to be in multiple level mode. Otherwise, you'd have to copy the loads that are placed on this particular level. So if I go back to multi-level, and let's say I just select all of my slabs. Here, window selecting selects everything, or I can use select by type, which lets me isolate. So I'll select slabs, and we're going to add under loading, we'll add dead load. We'll use 10 PSF for dead, and we'll use 40 PSF for live. This live load is unreduced. I'm going to show you how to set up patterns so we can pattern the load. A disclaimer and a warning, pattern loading is well, I should say it was built for single level analysis. It was never, it was introduced long before multiple level modeling in the program. And so single level analysis really pertains to single level. There are ways you can set up patterns to associate with multiple levels, and I'll walk you through this. So here we have Marcus, the content today, the question was, can we add lateral loads to make it more interesting? The webinar was marketed as gravity only, so we have videos that represent lateral loading. You can go ahead and look at those. We just don't have the time to go through lateral at the moment. We can set up any webinar we need to, but yeah, that's the premise of today's webinar. So just continuing on, we'll go back to patterning. So let's take, for example, level P3, and we've added dead and live load. I'm going to go to my default display. Under loading, we're going to go to subregions. So we need to define regions on the slab that we want to be able to select to pattern load to. Okay, so I'm going to basically, I'm going to click here to here, that will create a line, there to there, that will create a line, and so on in both directions to break this up into what we call subregions for patterning. Okay, so this is my first subregion, and I can turn on the orthogonal option. And then in this direction, I'll just follow these beam lines. You could also define these by drawing in polygons, closed poly regions, to define every single subregion. I use this method because it's just easier to break these using these lines that are intersecting. So those are my subregions. If I go back to load patterns, you can see each subregion contains a handle. And when we break this into patterning, we can now reduce the load horizontal, the load that's applied to the horizontal elements. So in this case, the load case that we want to reduce is live load. We'll set it up to reduce, and we can also include a skip factor. This might be 0.75, let's say. And this factor gets applied to the live load when it's applied inside of the pattern. Okay, so my first pattern is going to be all subregions selected. There's pattern 1, and it shows a hatched view of the patterns. Pattern 2 will be something like this. Okay, pattern 3 we'll say is this. Pattern 4 we'll say is something like that. We'll say this is pattern 5. And then pattern 6 we'll do one more, pattern 7. Okay, so we have 7 patterns. I can copy the subregions to other floors, but in order for me to actually include all of my patterns in a global analysis run, or even single level run, I would have to name those patterns differently. So here I have, 6 floors. I would have to create, let's assume we start at level 1, that's patterns 1 through 7. Level 2 is patterns 8 through 14. Level 3 is patterns 15 through 22, and so on. And those patterns then have to be set up in every unique strength and service combination that you want to include them in. So you can see it becomes data intensive when we want to add patterns to multiple levels and be able to process those patterns individual to their own floor or globally to a global run when we model this globally or run it globally. So this is only pertaining to one floor, which here is level 3. And once that patterning is set up, I'm just going to save the file here. Okay, once the patterning is set up under load combinations, we have the patterns dumped into this dialog. Now, something that's important, and I want to be clear about this, is the following. Skip live load max and skip live load min, which is just the envelope of the patterns, are only applicable to the general analysis, meaning if you set up combinations with skip max and min, you can review deflection contours, you can review any analytical result, beam moments, column axial forces, etc. for enveloping, skip max and min. For the design of sections, when you generate design strips and you process the strips for reinforcement, for stress checks and so on, those must be set up individually per pattern. The reason for that is when we process the design sections, we basically integrate over the path of a section. So I'll give you an example. If you have a slab, let's say this is a portion of a slab and you have some elements in here, and these are just shell elements. Maybe there's beam elements in there too, and let's say your design cut passes through this strip. When you press the button, design the design sections, the program takes each cut and it integrates over that section length. So max and min here don't work, because when we integrate, we have to basically take and determine what's happening at every single node that this passes through. So if this node and this node, and let's say there's a node over here, let's assume this node here is called 1 and this node is called 8. Node 1 could be controlled in terms of its skip max min by pattern 6. Node A could be controlled by pattern 5. So if you integrate across there, you're not integrating potentially for the same pattern when you use skip max and min. That's why we recommend to use patterns 1, 2, 3, 4, 5, 6, 7 when we set up our load combinations for the design of the strips. Okay, and it's 100% related to the integration method that we use for the section results. So what does that mean in terms of setting up our combinations? That means for each combination that we want to evaluate, we need to evaluate this for 7 combinations. This will be strength, dead and live, pattern 1 all the way through 7, strength, dead load only, 1 all the way through 7. So this kind of gets expanded and it starts to scale up based on the number of patterns. Okay, in our case, we're going to leave this set to live load over the entire slab. I'm not going to set up the patterns just for sake of time for these combinations, but I wanted to give you just a flavor of what that looks like if we use patterns for this type of a structure. All right, let's go ahead and continue on here. I'm going to leave those in there. I'll just go back to my default display. Additional combinations. These are gravity only combinations. The question was asked earlier, can we set this up for lateral? If we did set it up for lateral, then obviously we would need to introduce more combinations in the dialog that include gravity and lateral effects, and we could use the wind load wizard, seismic load wizard, lateral load wizard to introduce lateral loads in combination with the gravity loads. Let's go over now to criteria. We're going to set our concrete strength here to 5,000. We're just going to use concrete 1 for today's session. And then rebar, we'll change the modulus. This is actually opened in, it shows PTRC here, but there's no tendon dialog, and the reason for that is I had opened up another model in RC mode. So what we want to do is close this. I'll close that example model, and I need to reopen Builder in PTRC mode. So I'll reopen the program. I'll switch this over to PTRC. It's already set because I had first opened the model we were working on in RC mode, and then I opened another one in PTRC. So I'll just reopen this model in PTRC, navigate back to level 3. Under criteria, you'll notice now we have our option for post-tensioning for PT. So pre-stressing, we'll change this maybe to 28,500 for the modulus. These two don't apply today. Design code, we can set whatever design code it is we're using here. We'll say that for one-way beam and one-way slab and beam criteria, the strength reduction factors get filtered based on the criteria. So just make sure that you set the proper. These should be code related. If I set this to ACI 14, for example, you can see shear one-way 0.75, 0.75, two-way shows 0.75 also. We'll talk about rebar lengths and some of the rebar criteria as soon as we get to the design. That will be in part 2, so we'll leave some of that alone. I want to talk a little bit about the analysis and design options. For all of our support lines that we're going to set up today, they're going to be either beam or one-way slab. So my recommendation is anytime you have a model that includes beams, I would use this option to include the waffle or joist construction. That just ensures that if you have a column, and let's say you have a beam modeled, and let's assume your support line goes over the top of that beam and it snaps at this column. It doesn't snap on the endpoint of a beam. In earlier versions of the program, 17 and prior, if you had a model like this and you cut this element like so, here's my design cuts. When we look at those design cuts, if we use regular floor system, these cuts physically look like this. It's a T-section, but analytically we assume that this is a structural or a architectural beam. It's included in the analysis. It's discretized in the frame elements, but when we analyze and design the section, we actually avoid using the beam stem. This goes away. So this is what we call the physical cut. This is called the idealized cut. And this is what we use for generating stress checks, rebar, and so on. So you have to be careful. If you want your beams to be represented as structural beams and this stem to be included as part of this cut that we evaluate in Designer, you either have to make sure you set up the support line so it snaps to at least one beam end. So this beam I would actually move to the center of column, and that's how this model is set up. Or just turn on waffle construction, and that means whenever a section cuts through a beam, the stem is always included in the Designer when we design that. So this is kind of a global setting that we can use for that purpose. For the support conditions, since we're running this in single level, the support is a roller support and rotationally fixed. If we want to modify that, we can to something different. If we run it in global mode, the support condition is multi-level. And make sure if you have this option selected, which by default it is, retain user modification and create everything else as below. What this does is the program, if I'm in single level mode, let's say, and before I analyze, I'm actually going to create the supports so I can see what the program is creating. This is not required, by the way. The program will automatically create them. I'll just create my supports. And let's say that I want to change this wall in single level mode for some reason to fixed. That is a user modification. I just user modified that support. If I now go back and I rerun this model in multiple level mode, that support will be retained. That will stay there. So let's assume we had lateral load in this model and I had done just that. You're going to see, shear build up in these walls as you move vertically down, and then you're going to get a diagram that's basically zero because we have a support there. So if you ever user modify a support, just make sure that you go back and at this particular level, I'm just going to simply delete it. I can go back, delete that support. When I go back to multiple level, the program will again auto restrain the base of the structure using the settings under analysis and design options, and you don't have this issue. So that's one thing to be careful of. If you don't want the program to ever retain user modified supports except for the instance that you're running the model in at that particular time, you can always deselect this to avoid that in all cases. Okay. Other things that may apply to one-way slab and beam. Twisting moment is generally applicable to two-way slab. Reinforcement larger than strength, or excuse me, larger than cracking, is applicable to bonded systems. This model, we're going to use an unbonded PT system. And then if you wanted to consider the PT only for deflection, but let's say you wanted to design a beam as an RC beam but use PT for deflection, you could actually use this option here. Another thing that might come up, if this parking structure, which lots of times they're moment frames, if it's in a higher seismic design category and you have to restrict the capacity in the moment frame generated by the PT beam to some percentage, then you could use this option, check if fraction of bending strength of a beam is provided by pre-stressing exceeds some number. So this is 25%. This means that if I use this option, the program will actually report the amount of rebar needed to dilute the capacity contribution to 25% from the PT beam. That's reported in the output. So that's something that sometimes is applicable to these types of structures that you may have to account for. So that's a few interesting things there with the analysis and design options. The allowable stresses, again, those are also specific to the criteria. For a two-way slab, it's set to 6 by default. For one-way slab and beam, it is set to 7.5. If your beam designs are, if you're allowing a greater allowable stress for beam design, you can always modify this value. If I run the model and let's say our stress is 8 square root of F prime C and it says it's no good, but we can go up to 9 square root of F prime C for some reason, then in order to avoid the no good, we have to change the target. We have to change the allowable stress in this dialog. And so there are ways to consider that. Okay, so we've shear design. For shear, we're going to look at one-way shear reinforcement. So this is based on, I would call it the simplified equation for shear for one-way slabs and beams. The program will check the slab if it's a one-way slab, similarly to a beam for one-way shear. Two-way shear doesn't apply. If we want to set the reinforcement size for one-way shear, then we set that here. For one-way slab criteria and beam, by default it's set to 5. I'm actually going to change it to 4. One-way slab shouldn't fail in shear, but at least not in this example. One-way shear for beams, I'll set that also to a number 4. Okay, so let's now talk about strips just for a few moments. We'll go another 8 to 10 minutes or so, and then we'll open it up for Q&A. So we'll get through some of the strip modeling. It's pretty clear for the beams we need to define beam strips. So that's a fairly straightforward requirement. The beams are oriented in the Y direction, so I'll use Y support lines. And we're going to go into the properties of the support line and make sure that this design is set to beam. Okay, if we want the beam criteria to apply for reinforcement and for stress checks and so on, this has to be set up properly. So we'll say beam. You can also see this is set to inner layer for top and bottom rebar. And let me back out of this dialog for just a sec, and I'll go back to criteria. If we look at the rebar options. Actually, it's under cover. Let me go to rebar cover. The minimum bar cover to the top fiber is 1.5. Minimum bar cover to bottom fiber is 1.5. So the way that the beam was set up to be inner layer, if I look at this beam, and let's say we have our longitudinal bar here, and maybe we have a longitudinal bar here, this cover to longitudinal bar is 1.5. So we would want to first add in the diameter of the stirrup to these covers that we set. But in addition to that, because the program is calling the beam strip a inner layer, it's actually adding, in terms of the effective depth to this direction, let's call this D, it's adding the cover 1.5 plus a full bar diameter, because it's assuming, because it's inner layer, it's actually, there's a bar in the transverse direction. And that bar in the transverse direction is based on the bar size at the top or bottom. In this case, it's bottom. So the effective depth in this beam design, if this cover is set to 1.5 and we have an inner bar, that cover is actually going to be 1.5 plus 1. It'll be 2.5, which is too much, right? This will become conservative in this case. So what we would want to do, let's assume we actually want to cover to the stirrup of 1.5. We're going to add in the stirrup diameter. So we'll say that this actually becomes 2. We'll just say 2 top and bottom. But we want to make sure when we set the strip up, I'll go back to the properties of the strip. We change the properties for the beam, and you can see here, yeah, notice, where is the design? Yeah, the properties are gone there. I think I need to, there should be inner layer, outer layer. I don't know where they've gone. I'll have to check that. But make sure that the proper layer is set in the dialog. So let's change that back to beam. Okay, and we'll go ahead and just draw. I'll draw one of these. I have the supports turned on, so if you have sensitive snapping, here I have sensitive snapping, I'll call it, because I have snap to vertices of components turned on. What does that mean? That means when I try to snap on the corner of that slab, it's actually picking the corner of other components. If I turn that off, then it will just snap on that corner by virtue of having the snap to endpoint turned on. So we'll go from column to column. This is a beam support line. Okay. In this example, which is often the case with these types of slabs and one-way slabs and beams, I really only have to model one, and then I'll just copy paste it over multiple times. If the spacing is equal in the X direction per bay, you could also use modify copy paste multiple times. So those are the support lines for this direction. If we generate them, you can see they're all set like so. If you notice, these are full tributary strips. So let's assume you say, well, I want to model the beam with an effective flange. And okay, so how do we do this with an effective flange? Well, we would have to isolate using splitters. So I'll use a Y splitter, and let's assume for these beams, I want my effective flange to be this dimension. Now, I could put dimensions in here, and I could click on the exact point and make sure I have the exact distance to either side. But here, these are just arbitrary splitters. Now, if I take these and I'll use Control-Shift-C to copy from a reference point. Let's assume for every internal beam, I want something like this. And then I go back and I generate my strips. Notice that we have voids in the slab. So if you do this, the program will say, okay, we'll cut the flange back down, but now I have zones where I have actual voids in my in my slab. In other words, we're not going to get results for these portions. I'll call them middle strips, even though it's really not a middle strip in the sense that it's a two-way slab. But if we want to design this portion, then we have to set up another series of strips. So I would come back and I would have to generate more support lines. Okay, I would do maybe support line like this. And again, I can copy this using a reference, and I'll just use this column. Okay, now I have middle strip support lines. If I regenerate, I have a beam strip and a strip in between in the slab. So this, I mean, this might be called a one-way slab strip. I don't know what you would actually call it. So these strips are designed based on whatever is intersecting them. And in closing for today, before we go to Q&A, if we have tendons in the beams, I'll just draw some tendons in. Let's say we have tendons here and here. Those sections that look like this with a tendon in them are designed as beam PT. These are designed as PT beams. If we look at this section in between beams, which is just a slab, that's actually designed, let's say I define it as a one-way slab. This now gets defined as one-way RC. So this gets designed separate from this. Let's say we put in temperature shrinkage tendons inside of this slab. If you put tendons in there, then it goes back to tendon PT. So you have to make sure that for a system like this, if you're adding temperature tendons in the slab, make sure they're distributed inside of those strips that are in between beams if you cut the beams off using an effective flange. Okay, and then next week we'll pick up where we actually model the one-way strips. We're going to model just a uniform strip in the X direction and copy that over multiple times. And then we'll add PT to this and process it for the stress checks and the design for gravity. But we'll reserve the next 10 minutes or so for questions if there are any. Again, I appreciate everyone's attendance today. This again is part 1 of 2. So if you've set your calendar for next week, we'll continue on. But if you have questions, feel free to just chat, submit the questions through the chat panel in the floating panel. For those of you that need to go, again, I appreciate it, and we'll conclude with the main presentation today. Thank you. Okay, there is a question. Can we design a beam I section in ADAPT Builders? This is a good question. You cannot directly design a beam I section in Builder. You would have to use ADAPT PT to do an I section. You could. The reason for that is in order to create the flange on the bottom. If we if I let's say I have a slab. This is at reference plane, let's say 3, and then we have a stem. And then in order to create this element for the bottom flange, let's say the bottom flange needs to look like this. This would have to be a shell element. So it could be a frame element. We could create a frame element out of this shape. I mean, that would be something we would do to allow this potentially, further in development. But right now, this has to be a slab. So what happens is if slab 1, I'll call this top and bottom, are both referenced off of plane 3, we can't mesh this because there's a gap between these two flanges. The program will give you a warning and say you can't mesh it. So the only way to really do this is you could create another plane. We'll call this 2.9. And if I created a separate kind of a sub-level in the model, I could model a flange, a wall, and a flange, and then it almost becomes like a waffle in a way. In this case, you can analyze it, but you still couldn't design it, because in order to design it, you have to have strips and support lines, and those only really relate to one particular level. So if you add a support line at this plane here, it's only going to consider what's connected and referenced from that plane, which would still be something like this. So that's a current limitation. You can model I-beams and design them inside of ADAPT-RC, which is our 2D program. Thank you, Miriam. There's another question. Should we just model one continuous support line in the Y direction, even if we have discontinuity in slabs, or should we do two separate slabs? That's a good question. So in my case, I modeled it continuous. It really can be done either way, to be honest. I think both ways are equal. I guess the downside to modeling it as a continuous support line would be, let me turn off the strips here. If there's a true break in the slab here, and in the end, you know, the result you want is maybe not post-tensioning, but PT and rebar, and you say, okay, well, I want rebar. So if it's continuous, the rebar would technically be shown graphically like this, passing through that joint. If it's split, then you'll basically have two rebars. You'll have one here and one here. So it's more true to representation if you break the support lines. One reason you would draw them continuous is if you break support lines in today's version, in the next version, this won't be the case, but if I break these at this point, then I have to put splitters along here in order to get the right tributary regions on this side and the right tributary regions on this side. Rohan, I think that answers that question. If not, just let me know in the chat. Thank you. Other questions? Yeah, if we have a one-way slab, can we modify the stiffness so that you force the slab to basically behave one way? That's the gist of the question. Yes, you can. You could say that this slab, if I go to stiffness modifier for the slab and say edit usage, I could add a new usage. So I might call this one way. And then for that slab, I could define modifiers here. So let's assume we want the slab to flow in the X direction only. So we want to release the bending, let's say about 1:1. I would just set this to something very small. And then when we analyze the slab, when I mesh this and finally analyze it, you can select which modifiers you want to apply to that analysis run. So here I would select one way and then run it that way. And that would, all of the results would be premised by that stiffness modifier set versus uncracked, which is just set to 1 for everything. You could store multiple modifiers in here and run the model multiple ways in the same model. Thank you, Miriam. Other questions? All right. It doesn't look like we have any more questions. Again, I appreciate everyone's attendance. We'll go ahead and conclude now. I'll add this to the webinar page. It looks like one more question may have come in. When will we post the sessions on YouTube? I will post them as soon as the video is compiled from GoToTraining. It should be up, I would say, within the next hour or two. There was another question about copying, pasting components from one model to another, but it didn't work. Marcus, I will answer that in a separate email to you. Doesn't apply to this particular webinar. So I'll send you a short video showing how to use that function. There was a comment for the previous two-way slabs. They couldn't be found. Let me go ahead and show everyone where we can find those videos. If we go to youtube.com/adapt support, if you go down to playlists, and under the playlist, there's ADAPT webinars. So if you go into the ADAPT webinars playlist, I'll pause that. Let me go back and see if I can see the full playlist. Where's webinars? Okay, here we go. Full playlist. So the last two, these are not sorted in any real meaningful way, I don't think, other than maybe by date. But here, if you look at, this is 2ARC flat slab in Builder 18. This is last week's. This is part 1 and 2 of the two previous. So these are in sequence of adding them to the screen. If you go to the bottom of the list, they should be there. One is they're all about an hour and a half, hour to an hour and a half. All right, I appreciate everyone's time. Thanks again, and we'll talk to you soon. Thank you.